Alright, so in this video we are told that water flows through the converging fitting and discharges freely to the atmosphere. Assuming the flow is incompressible and the friction is negligible, determine the gauge pressure at the inlet of the fitting given that the diameter of the inlet is 150 millimeters and the diameter of the outlet is 75 millimeters and the velocity at the inlet is 1.2 meters per second. So in my diagram here, I've labeled points 1 and 2 of this converging fitting, and I've also added in some symbols for our known values, our inlet diameter and velocity, and our outlet diameter and pressure. So in order to solve this problem, we're going to try to apply Bernoulli's equation. Now, in order to use Bernoulli's equation, you have to have the following assumptions: steady flow and streamlined flow. And we're told in the problem that this fluid is incompressible and that friction is negligible. And with negligible friction, we can assume that the fluid is inviscid. So, the version of Bernoulli's equation that I commit to heart is the head form of the equation. Now, since this pipe is oriented, or this fitting is oriented horizontally, we can neglect the change in height, which is the z term of this equation, since they are going to be equal. We also know that the pressure at the outlet, the gauge pressure, is the atmospheric pressure, which means that the gauge pressure at the outlet will also be 0. Now we're left with 3 terms in our equation. A term with P1, which is what we want to find. A term with V1, which we know. And a term with V2, which we don't know. In order to solve for V2, the velocity at the outlet, since we know that the fluid is incompressible, we can apply the continuity equation. Which states that the flow rate at the inlet is equal to the flow rate at the outlet. Flow rate is determined by velocity times area. And in this equation, we know everything except for V2, so we can solve for V2. Areas are equal to pi by 4d squared. Now the pi by 4 will cancel. So V2 equals our inlet diameter times our inlet velocity. Now calculate this. 0.15 squared divided by 0.075 squared times 1.2. We get that our outlet velocity is equal to 4.8 meters per second. Now back to our pressure equation. If we solve for P1, I'll write it like this first. So I just subtracted V1 squared on 2G from both sides. I'm going to multiply I'm going to erase this. Move this over here. P1 is equal to and my algebra step here was multiplying both sides of the equation by gamma, or specific weight, and factoring out this 2G simultaneously from these terms. Now, since we have specific weight divided by gravity, it might be helpful to note that specific weight is defined as density times gravity. So when we divide specific weight by 2G, we can simplify this a bit more since the gravity terms cancel out. So our first term can be reduced to density divided by 2. So now, since we know everything that we need to solve for the gauge pressure at the inlet, we can assume the density of water to be 1,000 kilograms per cubic meter. V2 is 4.8 meters per second squared minus 1.2 meters per second squared. Calculate this. We get that our gauge pressure is 10,800 pascals. Now maybe you are skeptical about how I got pascals as a unit. So I'll show how I got that. Always want to verify our units. So essentially in our pressure equation we have kilograms per cubic meter in this term, square meters over square seconds in this term, and also square meters over square seconds in this term. So our units are this for P1. We can rewrite this as kilogram meter per second squared divided by meter squared. Simply letting one of these square meters. Cancel one of these, leaving meters squared in the denominator. And this term is a Newton. This is a Newton per meter squared, which is equal to a Pascal. So our final answer is 10. Ooh, that's large. 10,800 pascals. So thank you for watching this video. Subscribe if you're new for more engineering practice videos. Thank you for your time and have a great day.